Good evening to all of you. Dear Imam, can you hear me? Okay. So, you are the only one student. Where are the rest of the students? Wait a minute. I will give you the permission. Wait a minute. Yes, Imam, you can tell.
Hi, Dr. Faisal. How are you?
I'm fine. What about you?
I'm fine, thank you. Doctor, I want to tell you, I sent you the assignment, but I sent you without details. I received.
I received your mail today. Today or yesterday. I have received all your mail.
It's just 8 and 10, yes. Yes.
Okay, it's all right.
Okay, thank you.
Okay, welcome. So let's start our topic. Wait, I'm going to download the PowerPoint slides. चेक करिए मेरा हेडफोन, अपना हेडफोन चेक करिए, योर हेडफोन इज अवेलेबल। इवन मेरा नहीं लग रहा, मैं उस कमरे में ड्राइविंग में छोड़ दिया मैं। आई फॉरगेट माय हेडफोन ऑन जी। ओके, so today is our lecture based on linear transformations. So we will proceed. First of all, I'm going to discuss what is transformation. The transformation this is the definition of the transformation. Transformation of function T maps of a vector space V into a vector space W, and it is denoted by transformation of V to W, and V and W are the vector space. So V is a domain and W is a codomain. So this is the concept of the linear transformation. One is domain and another one is codomain, and we have to transform the elements from V to W, and where the elements are going, it is called the range. This is the range, and this whole part is the codomain. So this is called the transformation. So there are so many things we discuss in this transformation, like there are some terminology of the transformation, like what are the kernel, what are the range, what are the rank, what are the range. So these are the terminologies of the transformations that we use in this. So one by one we discuss. First of all, we discuss some questions based on the transformation to show that whether it is a transfer. There are one type of question is that there is a transformation is given, and you have to show that the given transformation is valid or not. And another type of question we are facing, that show that is it a transformation or not. So one by one we will see the whole thing. So one by one, the image of V under T. First of all, we will see some definitions, some terminology of this. If V is in V and W is in W, such that transformation of V is equal to W. Meaning is that if we have two sets, and so it says that if V is in V and W is in the element W is in W, capital W, and V is in a small v. V is in a small v and W, such that transformation of V is equal to W. Transformation, when we are going to transform, then it will be W. So then W is called the image of V under T. W is called the image of V under T. So this is the range of T, the set of all images of a vectors in V. Similarly, the pre-image of W, the set of all V in V, capital V, such that transformation of V is equal to W. So this is that some terminology you have to. Fahad, what do you say? You can't see the PowerPoint slides, but it is available on the blackboard. You can see it clearly. Okay. So these are the terminologies of the transformation. So keep in mind, whenever we talk, what are the images, what are the range, what are the pre-images, what are the transformations. So just keep in mind, there are two sets, V and W. The element in the V is small v, the element in the W is we denote as small w. So we will discuss rest of the things are later. So there is a very easy question. Question number 1, let there is a transformation in R2 to R2, and there is an element are given, V is equal to V1, V2 and R square, and transformation of V is given. This transformation is given. For example, it is equation number 1. And the question is, find the image of V minus 1, 2. So the image of V is minus 1, 2. We are going to solve A part. So image of V 1, 2. So we write transformation of V is equal to. So we apply the transformation on both sides, left side and right side. Both sides we apply the transformation, and we from equation number 1 we can write it. From equation number 1 we can write it V1 minus V2, comma here, and V1 plus 2 times V2. From equation number 1 we can write like this. So it will be equal to minus 3 and 3 from equation number 1. This is A. Now we see the B part. Find the pre-image of W. So pre-image of W, yani it is given that transformation of V is equal to W is equal to minus 1 1. It is given, and we know that transformation of V1 V2 is equal to V1 minus V2 and V1 plus 2V2 from equation number 1. We know it. So, and it is given that transformation of V1 V2 is equal to minus 1 1 1. It is given inside the question. So equate the coefficient. So this will is equal to this this one, and right side is equal to right side. So we equate the left side and right side and subtract them and find the value of V1 V2. So in this method we find the value of V1 is equal to 3 and V2 is equal to 4. Just 3 and 4 is the pre-image of W, means minus 1 and 1 1. So linear transformation. So now we will discuss the main topic of our main topic. What is linear transformation? So this is the definition of the linear transformation is, if V and W are the vector space, then the transformation from V to W linear transform, then it is called the linear transformation if these two properties are hold. Number one property is additional property. Any transformation of U plus V is equal to transformation of U plus transformation of V, and the multiplication property, that is the transformation of CU is equal to C transformation of U, where C is a constant, any constant. So these are two properties. Whenever you have the question like prove that whether it is a linear transformation or not, you have to show these two parts. If these two parts are true, then you say it is a linear transformation. Now see, let's. So a linear transformation is said to be operation preserving. So when these two parts hold, first one addition in vector space and addition in W. Similarly, the addition is scalar multiplication in V and a scalar multiplication in W. A linear transformation from transformation of V to V from a vector space into itself is called a linear operator. Verifying a linear transformation T from R squared into R squared. So this is a question. It says that verifying it is a linear transformation or not. Yani it's we have to show that whether it is a linear transformation or not. So we have to prove it into two parts, as we know that there are two parts to prove. So let us assume that in first class U1 is U is equal to U1 U2 and V is equal to V1 V2 in R square, and C is any real number. So now part one we have to show that we have to show that transformation of U1 plus V is equal to transformation of UV. So let us assume that there are two vectors U plus V is equal to U1 U2 plus V1 V2 and U1 plus V1 plus U2 V2, and apply the transformation on the both side, left side and right side. So apply the transformation on left side is and apply the transformation on the right side. So let's see what happens when you from equation number 1 when you apply the transformation. This is equation number 1. What happened when you apply the transformation? So the transformation is V1 minus V2. This is first you write V1. So I write V1. Then apply the minus sign from equation number. Then V2 from V2 here. This is V2. Then put the comma. Then I put the comma here. Then it says that again V1. I put V1 here. And then plus sign. Put the plus sign. I put plus sign here. And then put the 2. I put 2 over here. And then put the V2. And I put V2 here. So it is 2 U2 V2. So, okay. So this will now open the bracket. When you are going to open the bracket, so U1 minus U2, separate the U terms and V terms and take the common. and u1 minus u2 plus a and u1 plus 2u2. Separate the u terms and v terms. So whatever you see that it is the condition of transformation of u, and it is the condition of transformation of v. So our first part is proof. This is our first part. Transformation of u plus v is equal to transformation of u plus transformation of v. So this is the first part of the linear transformation. Now we have to prove the second part. The second part is constant term of transformation, meaning that we have to show that, first of all we assume cu is equal to cu1 and u2. So the second part we have to show that transformation of cu is equal to c transformation of u. So we apply the transformation on the both sides, left side and the right side. So left side transformation and put the transformation on the right side. Then according to equation number 1, I can open it. As you know, equation number 1, what is this? Is equation v1 minus v2 comma v1 plus 2v2. So I put this plus comma c1 plus 2v2. So take common c outside and u1 minus u2 comma u1 plus 2u2, and it is nothing, it is transformation of u. So therefore T is a linear transformation because of both the things are hold. So this is the proof of linear transformation. So there are some examples. So there are some definitions. What are zero transformation? Zero transformation means transformation of v to w such that transformation of v is equal to 0. Then we say that it is a zero transformation. And what is identity transformation? And when transformation of from v to v, then transformation of v is equal to v for all v belongs to v. So there are some little bit small definitions. Transformation of 0 is equal to 0, and transformation of minus v is equal to minus transformation of v. Transformation of u minus v is equal to transformation of u minus transformation of v. And it says that if v is a linear combination, then transformation of v is equal to c take outside, and transformation of v1 c2 transformation of v2 plus, and so on. So these are some small definitions that you have to memorize it. Now we proceed. The linear transformation and basis. So there are some standard bases are given. Transformation R3 to R3 a transformation be linear transformation such that there are some standard bases. It is called the standard basis 100, 010 and 001. These are called the standard bases. So there are some transformations are given, and the question said that find transformation of T3 minus 2, 3 minus 2. So we can write 2, 3 2, 3 what you can't understand, Mutaib? Previous question or this question? So let's see. Still I am not reaching 770. So you listen carefully. Then after you will discuss. So we have to find transformation of 2300. So we can write first of all it is a basis. So any basis can be written in. We know that any basis can be written in the standard form. So we write 2 into 100 and 3 into 010 and minus 2 into 001. This is a standard basis, so we can write here like this. And if you combine it, then you will get 2, 3 minus 2. It's okay. So now apply the transformation on both sides, left side and right side. So left side transformation and right side apply the transformation over here. So apply transformation here, apply transformation here, apply transformation both the sides. I apply the transformation. So but we know that transformation of 100 is equal to minus 214 from 1. From 1 we get 214, and from 2 we get transformation of 0, 1, 2 we can get 1, 5 minus 2, and from 3 we get 2 times transformation of 3 we get, it is not t, it is get 0, 3, 1. It is not 3, it is written wrong. So we get 0, 3, 1. So combine all them, we get 770. So now tell me what you don't understand, Mutaib. What is your question? How we can combine? Just as I told you so many times that there are if there are vectors I and comma j, and there are some vectors in other like j, k, and other vector l, then we have to add I to k and j to l. Yani we have to add ith element to ith element, jth element to jth element, and kth element to kth element, and so on. So here we have this element 2 to the 4 and 3 ones are 3. 4 plus 3, 4 plus 3, 4, 5, 6, 5, 6, 7, and 2 multiplied by 0 is 0. So what you get? 7. Similarly, you multiply 2 into minus 1 is minus 2, and 3 multiplied by 5, 5 3 is 15, and minus 2 multiplied by 3, what you get? You get 7. And again in the same matter you multiply 2 into 4 and 3 into 2 and minus 2 into 1, so you get the same number. So listen, be careful in a face-to-face class, because of I repeat this method so many times. So we have to add ith element to ith element, jth element to jth, and kth element to kth element, because of these are the vectors. Okay. So now there are some other questions. Find a linear transformation defined by a matrix r square to r square. We have to make the matrix from r square, yani second dimension to third dimension, r square to r cube, defined by transformation of v is equal to av, and it is given that show that transformation of v is equal to v is equal to 2 minus 1. It is given that the vector is 2 minus 1, and it says that find the transformation. So number A part, it is given transformation of A is equal to AV. It is given A into V. We write V here, 2 minus 1, and just multiply vector into column, first row into first column, and third row into third column. So we get 6, 3, 0. So it is a vector space. So transformation of 2 minus 1 is equal to 6, 3, 0. And the second question is show that T is a linear transformation from R square to R square. So here the question is T is a linear transformation. We have to show that. So what we have, we know there to show the linear transformation we have two conditions. First condition, we have to show that it is addition, and the second condition, we have to show that the scalar multiplication. If these two conditions are satisfied, then we say that it is a linear transformation. So there are some more definitions on the matrices. Let A be a M cross N matrix. The function T defined by transformation of V is equal to AV. This is a linear transformation from A to A. There are some definitions, and you will see at these PowerPoint slides. So what now? Next thing is what are kernel. So the definition of the kernel is let transformation of V to W be a linear transformation, then the set of all vectors V in capital V that satisfy transformation of V is equal to 0 is called the kernel of T, and it is denoted by kernel of T. Yani, or we can write in the mathematical language, kernel of T is equal to V such that transformation of V is equal to 0. So for your understand how we can draw this on a set. What this say that what it say that there, according to definition, what it say that the set of all vectors in, if for example if we have capital V here and W here. So what it says that transformation, such a transformation from V to W is a transformation. It says that transformation from V to W, and it says that the set of all vectors V in V. For example, there are some vectors V in V, such that transformation of V is equal to 0. Transformation of V is equal to 0. Meaning is that is called the kernel of T, meaning a transformation of V for all V belongs to V. Meaning is that there are some zeros are available in V. So if we are putting the transformation, then all the transformation are 0. This is the meaning of this. So this is called the zero transformation. Transformation of V is equal to 0 and V belongs to V. This is called the kernel of T. So there are some questions of kernel of T. Transform the kernel of the zero identity. The transformation of V is equal to 0, 0 transformation. The kernel of T is equal to V, and the transformation of V is equal to V. The identity of the transformation kernel of T is equal to 0. Find the kernel of a linear transformation x, y, 0. So r cube to r cube, it is given that, and it says that find the kernel of T. So transformation of x, where the kernel of T means 0. We have to find 0 here and 0 here, and whatever the point is on that side, that is 0. So here we get Z is a real number. So find the kernel of a linear transformation. It says that from transformation is given, and it is a transformation from R3 to R2, and it says that find the kernel. So we know the equation of the kernel is, kernel of T is, if we have vector and it is equal to 0. We know this is the equation of the kernel. This is the definition of the kernel. Transformation of V is equal to 0. So we have to find the vectors where this transformation is 0. So we write transformation of x1, x2, x3 is equal to 0. So transformation of x1, yani 3x is given from equation number 1. This is equation number 1. So transformation of x1, x2 is left side, it is given, and we know from the equation of the kernel it is equal to 0. So we can find the value of the whatever the value. So by the Gauss-Jordan method, by Gauss elimination method, we put the coefficients 1 here like this. These are the coefficients 1, -1, and 2. We write the coefficient over here and we put there, and from the Gauss-Jordan method, Gauss elimination method, we solve this matrix like this and find the value of x1, x2, x3, or we put it t1, t2, t3, t put the outside, and there is common 1, -1, 1. So kernel of T is equal to transformation of 1, -1, 1. T is any real number. So this is to solve. This is the idea to solve the kernel of, from the kernel of T. There are one theorem. The kernel is a subspace of V. The kernel of a linear transformation of V to W is a subspace of the domain. So transformation of V is equal to 0. Kernel is a non-empty set. And what is the theorem? The kernel of a linear transformation from transformation of V to W is a subspace of the domain. So the theorem says that we have to show that kernel is also the subspace. This is the question. So we know to show the subspace, we have to show two parts. Number one part, the addition property hold, and number second part, the multiplication property is hold. So the same properties we have. If we show these two parts, then we say that it is a subspace. So here we show that let u and v be the vectors in the kernel of T. So transformation of u plus v is equal to transformation of u and transformation of v, and it says that transformation of u is it satisfy it is a kernel, so it is equal to 0, and transformation of v is a kernel, so it is also 0. 0 plus 0 is 0. So u, because of u plus v belongs to kernel of T. Similarly, transformation of u is equal to C transformation of u, and transformation of u is a kernel, so it is equal to 0. So C into 0 is 0. So thus kernel T is a subspace of V. So, and the kernel of T is sometimes called the null space. Either we say kernel T or we say null space of the T. So let there is a transformation from R2 to R5 to R4. We define transformation of x is equal to ax, where x is in R5. So find the basis for kernel T as a subspace of R5. So as usual, we have to write the coefficient matrix. We have to write the coefficient matrix of, this is our this is our matrix. We have to write it in the form a slash 0, because of it is a kernel, and we try to solve it, and by Gauss elimination or Gauss-Jordan method, so we can solve it like 1 0 0. We know that it is a procedure to solve it. First you write 1 and rest of the part is 0, then you write 1 and rest of the part is 0, then you write 1 and rest of the part is 0. So this is the procedure to solve the Gauss elimination method, and finally we get this. So these are the bases of the kernel. So there are some more definitions. The range of a linear transformation. Let transformation of V to W be a linear transformation, then the set of all vectors W in W that are images of vector in V are called the range of T, and it is denoted by range of T. Range of T is equal to transformation of V. Yani if we have two spaces V and W, then the transformation from V to W, so the elements over here, particular elements are called the range of T. It is called the range of T. So this is the definition of the range of T. The range of a linear transformation of V to W is a subspace of W. Yes, of course we know. As we know, it is a subspace of W. Range is a subspace of W. As we see here, it is a subspace of W. So next, transformation of 0. It is it is no need to see the proof. So there are two definitions we see. Transformation of V to W is a linear transformation, and kernel of T is a subspace of V. Kernel of T is a subspace of V. Keep in mind what are the kernel and what are the range. So kernel of T is a subspace of V, and a range of T is a subspace of W, and it is a transformation from V to W. So there are some questions. Finding the basis for the range of a linear transformation. So there you can see these questions, and rank of that. So we will proceed our main theorem, that is we are going to proceed because of we discuss all the things, range, kernel, and rank. So combination of all these things, we make a very important theorem that is called the rank nullity theorem, or we say a dimension theorem. So we will discuss this theorem soon. So rank of a linear transformation of V to W. rank of T is equal to the dimension of the range of T. Yes, and nullity of T is equal to the dimension of the kernel of T. So these are nullity and T. So rank of T is equal to rank of A, nullity of T is equal to nullity of T. So the combination of these three definitions, we make the rank nullity theorem. This is a very important theorem, and it says that if let a transformation of V to W be a linear transformation from n-dimensional vector space V into a vector space W, then rank of T plus nullity of T is equal to n. This is called the rank nullity theorem or the dimension theorem. So, or we can say in rank of T, or you can say dimension of range of T, and in place of nullity of T you can say dimension of kernel of T, and in place of n you can say dimension of domain of T. So there are some proof are given, but you don't need to see the proof, just remember this theorem. And there is a question based on rank nullity theorem. Find the rank and nullity of a linear transformation R cube to R cube defined by this. So this is a matrix is given, and you have to find the rank. So we know by the rank nullity theorem, we know nullity plus rank is equal to n. Here, what is the rank of this matrix? We know the definition of the rank is number of non-zero rows are called the rank. So here number of non-zero rows are, one row is non-zero, this row is also non-zero, this row is 0, so our rank is 2. 2 is our rank. And what is the dimension of this matrix? Dimension is 3 by, it is this matrix is 3 by 3. 3 by 3 matrix. So n is equal to 3 and rank is equal to 2. So by the rank nullity theorem we can solve this. Rank is equal to 2 and dimension. So by the rank nullity theorem, as we discussed in the previous page, this theorem, rank plus nullity is equal to T. So we can find the nullity easily. So 3 minus 2 is equal to 1. So this is from the rank nullity theorem. So hope you understand clearly. Yes, it is whatever the matrix, whatever the if it is it must be a square matrix, not a 9 by 1. It is a 3 by 3, 4 by 4. It must be a 9 by, there must be a square matrix. So in place of n means there is a square matrix. So now we proceed. Finding the rank and nullity of the theorem. Find the rank and nullity of the linear transformation. So there are some more questions you will see at your home, how they can find the rank and nullity. So there is one question, and the answer is this. You can see at your home how they can find the answers. So based on rank nullity theorem, they find the answer. So we move. So there are some types of functions. So because of in face-to-face class we have a very less time, we cannot discuss such in detail. So here I can show you with the graph, with the figures, you can understand easily. So here now there are some functions because of in one face-to-face class I cannot discuss this thing one-to-one function. I just discuss the topic. So we know there are the functions one-to-one and many-one on to. There are so many types of functions. So when we have this is a definition: a function transformation of V to W is called one-to-one function if the pre-image of every W in the range consists of a single vector. T is 1 to 1 if and only for all U and V in V. Transformation of V is equal to transformation of U implies that U is equal to V. Then we say that it is 1 to 1 function like this. It is a 1 to 1 function. Every U can have a single image in W, but it is not 1 to 1 because of this. It has the two image, so that is why it is not 1 to 1 function. Similarly, the other onto function. A function transformation of V to W is said to be onto if every element in W has a pre-image in V. So 1 to 1 linear transformation. A linear transformation of from V to W be a linear transformation, then T is 1 to 1 if and only if kernel of T is equal to 0. This is the theorem. If whenever you have to ask that a question that show that it is this function is 1 to 1, so how you can show that this function is 1 to 1? So you have to show from this theorem. You just show that if kernel of T is equal to 0, then you can say that this function is 1 to 1. If kernel of T is not 0, then you say that this function is not 1 to 1. So there is no need for the proof, just remember this theorem. So there are some questions of 1 to 1 and not 1 to 1 linear transformation. A linear transformation from M to M given by transformation of A is equal to A transformation is 1 to 1 because of the kernel consists. The 0 transformation is not 1 to 1 because it's kernel. So there are some definitions. So the transformation of V to W be a linear transformation where W is a finite dimension 1. T is onto if and only if rank of T is equal to the dimension of W. So there is another theorem. If transformation of V to W be a linear transformation where W is a finite dimensional, then T is onto if and only if the rank of T is equal to the dimension of W. And if sometimes you have to ask the question, show that it is onto, then you have to show only the rank of T equal to the dimension of W. If it is true, then you say that it is onto. So there are two things. One thing is to show 1 to 1. If you have to show 1 to 1, then you have just show that kernel of T is equal to 0. If kernel of T is 0, then you say it is a 1 to 1. And to show onto, then you have to show rank of T equal to dimension of W. So there are some examples. A linear transformation from Rn to Rm is given by transformation of x is equal to x. Find the nullity and rank of the T and determine whether T is 1 1 or onto or neither. So dimension here one by one they solve. Dimension or domain of T is 3 and rank of the T is 3. Yes, we see it. And the nullity of T is 0 and it is 1 to 1. Yes, and it is on to 1. So one by one we see all this theorem. And the last topic is isomorphism. A linear transformation from V to W, that is 1 to 1 and onto, is called the isomorphism. Moreover, if V and W are the vector space such that there exists an isomorphism from V to W, then V and W are said to be isomorphic to each other. So two finite dimension vector space V and W are isomorphic if and only if they are on the same dimension. So there are some proof. Isomorphic vector space matrices of for the linear transformation. So this is a matrix is given to represent a matrix. 3 by 3 matrix is given, and you have to show that whether it is a linear transform or not. So there are 3 parts are given. This is the ith part, and this is jth part, and this is kth part. I, j, k are given, and we put it into the matrix form. So matrix for a linear transformation. So the reasons for matrix representation of a linear transformation, because of from this matrix transformation, it is very simpler to write, it is simpler to read, it is easy, more adopted for computer use. So that is why we use linear transformation. So this question we discuss in a face-to-face class. So for example, this is the question that find a standard matrix for the linear transformation r cubed to r square. Show that defined by txy is equal to x minus 2y and 2x plus y. For example, it is equation number 1. We have to find the transformation. So we know that find a standard matrix, a standard basis, a standard transformation is 1 0 0 0 1 0 and 0 0 1. These are called the standard basis. So transformation of E1 is equal to T100, and it is given that from T100 is equal to 1 2 from equation number 1. Why it is 1 2? From equation number 1, if you are right, यानी कि 1 minus 2 into 0 and comma 2 into 1 plus 0 and it will equal to 1 and 2 from equation number 1. Hope you understand how we get 1 2. Okay, so in matrix notation we write transformation of E1 is equal to 1 0 0 is equal to 1 2, or either we can write like this. Similarly, second transformation of E2, say 0 1 0. So we write from equation number 1 0 0 1 0. So यानी कि 0 minus 2 into 1 comma 2 into 0 plus 1. So what we get? Minus 2 1. So it is a way to write the transformation from equation number 1. So, or we can write in matrix notation, we write like this minus. Similarly, transformation of E3 is in the same way. From equation number 1 we get 0 0. So transformation of E3 is equal to 0 0. So this is the three columns. Column number 1, column number 2, column number 3. Combine these columns, we get a matrix. So this is the matrix, and this forms the transformation matrix. So this is approximately, and the composition of the transformation. This is the last topic, how we can compose it. If we have if you go from V to W, W to Z, then, or we can say that V to Z. So transformation of V is equal to transformation T2 transformation of V, transformation 1 V. So we write it, or we can say T2 0 T1, the domain of T or domain of T1. So like this. From this figure you can understand the meaning of this T2 or T1. So if we have two transformation of T1 and T2, then we say that it is a composition of a linear transformation. This is the definition of composition. Transformation of V2 is equal to T2 transformation of T1. So this is a proof. And there are some questions. Let T1 and T2 be a linear transformation R3 into R cube such that this is equal to XYZ. Transformation of 1 is this, equation number 1, and transformation of 2 is this, like this is. Find the standard matrix for the composition T2O T1. So standard, we can define the matrix as in the previous slides. We can write the matrix in the same manner. We can write this matrix, and in the same manner we can write this matrix from transformation number 2. So, and multiply this, we can see the whole transformation. So this is the end of your today's lecture. So you see these PowerPoint slides at your home, because if I upload these slides on your Blackboard, you will see these slides, and hopefully you understand. And your one more announcement: those students who are not sitting on the midterm exam, their re-exam will be scheduled on 13th of May. So if anyone is student who are not sitting on the midterm exam, they can appear they can appear the main exam again on 30th of this May. Okay, take care and good night.